Well, welcome everybody to this new section of the Simple Seminar course. Today, we're very pleased to have with us Professor Enrique Nadal Soriano. Professor Nadal is working at Universidad Politécnica de Valencia. His current lines of research deal with the application of numerical methods for the structural analysis of living tissues as bones, and also with topology and shape optimization tools. All this enriched with the use of machine learning tools. Today, he's going to show us his latest research on the Cartesian grid finite element method for patient-specific simulations. Enrique?
Thank you very much for the introduction. And also, I would like to thank Simne for inviting me here to come here today to give this talk to all of you. Well, first,
I believe you can take out your mask.
Thank you.
It will be easier for you.
Yeah. Well, the first, I will introduce my research lab that we start during the pandemic 1 year and a half ago. Well, today we are around 33 professors and 12 PhD students, and we follow these 5 research lines, which is railways, structural integrity, computational mechanics, robotics, noise and vibration. Myself and my colleagues work in computational mechanics research line. Okay. This line, the leaders are Professor Rodenas and Professor Tur, and we collaborate in the line. It's me, Enrique Nadal, José Manuel Navarro, and José Albelda. All of us are professors at UPV in Valencia. And also this year, Professor Oliver came to Valencia because he's in a sabbatical, so he can to share his knowledge with us during this academic year. Also, we have 6 PhD students and 1 postdoc working in this research line. And well, the work I'm going to present is, of course, part of the work of all the team. Well, which is the main idea? The main idea is that each day more models come from images. So we want to develop a software tool to easily analyze what's happening in the images regarding the structural analysis. There is a huge amount of 3D images that are being taken every day. And well, we want to develop efficient tools for the diagnosis or even verification. We started this work following the line in medicine for the structural analysis of bones, that the information comes from CT scans, but it can be also extended to any image captured by a CT scan or something similar. Well, the main idea at the beginning was to develop an efficient patient-specific in silico medical framework. For instance, if we want to introduce a prosthesis in a bone, in a mandible, for instance, we would like to easily handle this 3D image and also incorporate the geometry, the CAD geometry of, for instance, an implant into the image and check if it will work, this implant is fine, is not fine, what happened with the bone, what happened with remodeling, etc. Or if we can modify or improve the design of the implant. This was the main or the initial idea. Well, which problems we are having? The bone is very complex. In general, we have a compact bone and a cancellous bone with a very complex structure and with a very complex material distribution. Normally, with a CT scan of a human, we don't have this level of definition of the cancellous bone. Normally, it's diffuse. Also, we want to simulate how this bone evolved in time because we are facing a living tissue. Bone is a living tissue that is evolving. So we also want to simulate the evolution of the bone when we place, for instance, an implant. Well, in the standard finite element framework, we have from one side a series of CT images composing a 3D image, and also, for instance, a CAD model of an implant. Normally, from the CD image, with a very tedious procedure, we build a CAD geometry, for instance, in a mandible, and we put there an implant, and we can more or less specify the two kind of bonds, the cortical bond and the trabecular bond, giving some material properties to them. Then we construct the finite element model, and we can run our analysis as usual. What we want to do is to avoid this step in the middle, to avoid the generation of the geometry, of the full geometry from the CT scan, because when we build the finite element model, normally we forget about the geometry. Well, this is the layout of my presentation after this introduction. I will continue with the basis or the basic ideas of the cgFEM technology. Then I will apply that specifically for image-based simulations, and finally I will give you some of the applications we are developing today. Well, cgFEM the basic idea at the really beginning starts for an efficient finite element solver for optimization, for an optimization procedure, okay? Because the lower level in optimization framework, normally for elasticity problems, is the finite element method in general. We need a really high accuracy of the solution, or at least to control the accuracy in order to convert to the real or the optimal shape. For instance, in this problem, which is a cylinder under internal pressure, and the analytical solution is the gray area, we parameterize the external boundary with 4 variables. So, and we want to optimize the position of these 3 points, then we will obtain the optimal shape that should be the gray area. But depending on the accuracy of the finite element simulation, the area that the optimization procedure gives us could differ from the real, the optimal one. So it's important to control, and this control has to be really robust, because the user cannot supervise the mesh at each iteration of the iterative process. In that context, we can find standard finite element solvers, or we develop the Cartesian grid finite element method, because it has one advantage, that is that during the solving of the optimization problem, there are many elements that remain constant, and we can take profit during the optimization process from the previous calculations, and it's really easy to share calculation between individuals. Well, this was the main idea, and the cgFEM works as follows. There is a set of hierarchical meshes, and on the other side is the problem domain. So we put the problem domain on top of the meshes, and we build, taking some elements here in green from the set of hierarchical meshes, and we build the analysis mesh. This mesh is not conforming, as you can observe in these red points, but we use multi-point constraint to guarantee the C0 continuity required for the finite element, for the elasticity problem. Well, what happens here is that there are many internal elements and some elements around the boundary. So the internal elements are like standard finite elements. They can be integrated using the standard techniques. However, elements that are cut by the boundary require special treatment. So in general, there are some curves intersecting the element. There is an internal domain here in gray. We perform any triangulation you want, but this triangulation is just for integration purposes. It's not where the finite element solution lies. So we choose those triangles that are inside the domain, or we can choose all of them if there are several materials into the element. And this is the basic idea that is going to arise when we deal with medical images. In the 3D context, we also have the tool for the 3D context. We use the Martin cubes algorithm that classify the possible intersections of the geometry in a cube. We choose only those that only contains one plane. Otherwise, we can always refine the element up, and then we will time one surface. If not, we refine again and again, and that's all. So we just have these 7 preforms for integration. This is already pre-computed, since all the elements has the same shape, and this topology of the triangles will remain constant for this kind of integration. So this integration process is really fast, even for good elements. Of course, there are some elements that require some special attention, those that are several surfaces into the element, but this is normally a reduced number in a mesh. Well, we also consider the exact geometry, so the geometry provided by NURBS. And we can observe in the first donut is the geometry. The second donut represents the mesh where the solution lies, and the last one represents the integration mesh that is conforming with the geometry. So how we integrate this? We integrate with the cgFEM technology, which was has been developed in collaboration with Professor Ruben Sevilla. Well, what about the efficiency of this tool? Well, the efficiency, we contrasted, this is in the 2D case for the cylinder under internal pressure, and we compare the cgFEM technology with ANSYS, but this was done some years ago, it's ANSYS 11, and we have similar computational times for the cylinder under internal pressure. To be honest, 2 years afterwards, we try again the same situation, and ANSYS decreases in half the computational time. So ANSYS improved itself, of course. Not because we're happy with that. We don't want to be the best. We want to be something, well, in standard times, more or less. Well, but not all of things are good things. There is also some drawbacks of the technique, of course. Drawbacks comes because of the fact that the geometry and the mesh are not conforming. So the first point is how to impose boundary conditions there. So with Dirichlet boundary conditions are imposed via Lagrange multiplier. And if we follow the bibliography, there are many techniques in order to avoid the oscillations of the Lagrange multiplier space, which is really tricky to select. In our case, we follow an stabilization method based on the projection of the tractions of the solution through in the Lagrange multiplier space. So it's a stabilization method. We can observe that in this Lagrangian form, in which in the first part, in the first integral, is the stabilization for the Dirichlet boundary conditions, that we force that the Lagrange multiplier space is similar to the tractions over the boundaries coming from the finite element solution. And also, it happens that we have elements like this one that has only a small region of the geometry into the element. So the solution here in some nodes is not stable. So what we do is we extrapolate the solution from the interior of the domain through a patch, and we then stabilize the solution in those nodes that are far from the domain. So this is done iteratively in a Richardson framework, and well, in 3-4 iterations, it normally converges and gives good solutions. I have to comment that this iterative solver has a constant matrix, so it's at the end of the day, it's really fast. Well, these are examples for 3D models. This is a screw where we put some loads and some constraints. And this is an example of the mesh and the solution we can obtain with the technique. We also develop the contact algorithm with the advantage that we can really control the gaps since we are using the exact geometry. And we also need to stabilize the contact problem, of course. This is an example of 2 spheres, and we obtain the right convergence rate, also in displacement or in energy norm. Well, what happens since we are dealing with the exact geometry? That means that with very small number of elements, we can capture the gap and we don't have the standard tessellation of the geometry that could arise in the standard finite element framework. So we obtain very smooth results even with a very coarse mesh. We also developed the technology for the discontinuous Galerkin framework in 2D. Now we are developing that in 3D. And also we run topology optimization and hybrid optimization, which is a mixture between topology and shape optimization that we are developing now. Well, now going into matter to see what we can do with images. Well, when we integrate the stiffness matrix, at the end of the day, we have B, which is the derivative of the shape functions, and D, which is the material properties tensor. So what happened in a medical image? For instance, if we have a medical image, this is a 2D image, and I can highlight one element here in green. The red squares are, in this case, the elements. We observe that that element has, for instance, several voxels or several pixels in the 2D case into the element. So it happens that it's possible to correlate the color of the grayscale with the material properties via the Hounsfield scale. It measures the absorption of the CT scans, and then we can obtain the Young modulus for a given color in this framework. Well, we have we try several procedures to integrate these elements. One idea is, well, I'm going to put one integration point into each voxel, into each belonging to the element. But of course, when I reduce the number of voxels because I generate smaller elements, because the voxel mesh is constant, it happens that I end up with a very few integration points. So we think, okay, so we put into each voxel the required number of integration points, just in case that I will have only one voxel per element. Or we fit a smooth surface describing the material into the element. And well, this one in the middle is really accurate, so I get all the information, but there is a huge number, we could have a very huge number of integration points and really expensive. This is simple, but when the size is small, I have very few integration points, so I'm having problems in accuracy there. And the fitting-based technology, we are happy with that because, well, if I have a linear element, the variation of the material into the element could not be that high. So we fit a linear or quadratic surface, and it's not. So we can control the number of Gauss points, and this number of Gauss points is independent on the size of the element, and we can then pre-compute many things in the code. So how the procedure works? Here, if I have this is one element into the image, and you can observe that perhaps there is a really big variation in the grayscale. So this is not desired because I will somehow homogenize too much. So we perform first and each adaptive mesh attending to the color in order to provide more or less a constant material distribution or almost constant material distribution into the element. And we don't need to explicitly define the boundary, since the boundary at the end of the day, it's where there is a high gradient in the colors and they are implicitly captured by the refinement process. So this is, well, we start the code testing this. Well, actually, this X-ray image is from the Juanjo son. He was playing rugby, and he was a really big source of medical image in that moment. So we take profit of that. So his finger actually is the annular finger. So, and the procedure is really easy. We don't need to define the geometry of the bone in this case. We only need to define the geometry or the region where we want to apply boundary conditions. Okay? We run the finite element model, we apply the boundary conditions there, and we can evaluate what any quantity you want here in the region of interest, which could be, for instance, the bone. Well, and what about efficiency in generating the finite element model? Well, this is a mandible, only we represent 1/4 of that. It has around 1.5 million elements, and it has been generated in 55 seconds in MATLAB. So we can generate the finite element model really fast without having any kind of geometry just from the image. Well, and what about accuracy of this, which is always important? So we go to our preferred problem, which is the cylinder on internal pressure. We voxelize it. So we know the geometry, can make voxels from that geometry, and we see what happens. Well, if we solve the problem, we obtain that, well, since the geometry is not represented by a line, we have some inaccuracies along the geometry, of course. Well, you can say here, I'm having 4 times 4 voxels into the element. We can go further, 2 times 2, or even 1 by 1, or even many elements in one voxel. It's possible. But what's happening? That the problem, we have a geometrical issue, that we have stress concentrators here because of the voxelization. So it's not clever to go for a very, very refined mesh. What we observe is that if we, for the linear elements, we go for 2 or even 4 times 4 or 2 times 2 voxels into the element, we get more or less the right value of the energy. But if we go further, what we do is we go for solving another problem. What problem is the one? We are solving the problem with stress concentrators in the boundary captured because of the pixelization. So what is important is, in order to make a smooth capture or to swap up, to make smoother these concentrators, what we need is to make a smoother representation of the geometry by means of including several voxels into the element. Regarding to the convergence, we observe exactly that. At the beginning, with many, at the beginning, it's the left-hand side of the picture, having many voxels to the element, we have more or less the right convergence rate according to linear or quadratic elements. But when we make finer and finer meshes preserving the pixelization, that is the geometry definition, we convert or we stop the convergence rate because we are solving a problem which is not a cylinder in internal pressure, but is the pixelization of the cylinder. Well, and because of that, we always try to put at least 2 times 2 voxels in each element at minimum or even more. Well, what are the applications? The first thing we test is with aluminum foams. These are very complex geometry in general, but we can and has several applications today in aeronautics or in many situations. Well, by construction, they inject some kind of air or gas into the aluminum when it's melted, and well, depending on the deepness of the aluminum foam specimen, it changes. For instance, this could be the one that is in the bottom, but since the density, or well, since the weight changes, the porous changes with the height. Well, here we have several examples of the aluminum foam following with the position in the manufacturing process. So the first thing we try is, well, can we characterize it? Well, we have this is like a 2D image. We perform the mesh. Here is really easy. We have black and white, so it's easy to detect. We run the finite element solution. This can be done really fast. I don't have to generate the geometry of the aluminum foam. And what about accuracy? We know by experiments that there is a relation, which is the black line between the porosity and the material properties. The blue points are the tests that we numerically run, and we obtain a correlation that they are following the same curve. So more or less, we are obtaining what is expected. So it was a kind of validation of the technique in this case. Well, then we start now with the medical applications. We get confident with the tool, and we start with the medical application. The first thing we did is, well, try to predict, or at least to give some more information to the doctor for the hip fracture. Normally, this is the result that we find in the doctor, and well, depending on the bone mineral density in the region that is here, okay, the doctors decide if you are in a high risk, in a low risk of suffering from a hip fracture. Okay? Well, if you are placed according to your age or according to your bone density in the green zone, there is low fracture risk. In the red zone, high fracture risk. And this is more or less the analysis we have. But 40% of patients diagnosed with low fracture risk, they will suffer from a fracture. So what's happening here? So we have 40% of patients that we can perhaps say something more. And one of the ideas is that the bone mineral density is a mean value in an area, but it has not taken, it doesn't take into account the geometry of the bone or possible local defects. Well, what we propose is to use the Cartesian grid finite element method for medical images, and we just define or eliminate the regions that are not of interest. We can apply a load, since the load is far from the neck. Well, we can, it's not that important how we apply the load since we are far, but what we want to do is to relate the load with the weight of the patient, of course. We generate the finite element model, we solve it, we obtain a stress distribution. This is not stresses, actually, they are indicators, because actually the problem is 3D, this is 2D. But at least we have an indicator of the stress field, and it takes around 1 minute. So it's really fast. The user only have to define, well, more or less where the bone is finished in this green line, and also the weight of the patient. Other things can be done automatically. Well, what information we are now taking into account? Well, the bone characteristics at each point, because we integrate what is happening there. Possible local defects, if there is some part of the bone that it has a lack of bone mineral density. The geometry, the length or the neck diameter. Also the weight of the patient. And we can also improve this with artificial intelligence, with some clinical data. I have to say that we also try to include the clinical data, but the problem is that we have the images from some patients and the data for others. So it's really difficult to mix this, but that sometimes happens because it's really difficult to find data in the clinical context. Well, but in this case, only taking into account the structural analysis. This case are 2 patients that suffered from fracture. The first one was in green, and the second one was in red. So fracture 6, the doctor said that you will suffer from fracture. Fracture 1, doctor say you are safe. Well, the bone mineral density for the first one is really high, but well, look to the weight of the patient. It's not the same, and the stress indicator in the two of them, it's similar. Okay, so it gives more information that was not in the bone mineral density. Here we have two situations with no fracture, with very similar bone density, and with very different stress indicator. Look to the shape of the bone neck is really different, and also the weight of the patient is different. So we can, to handle it, take all this information into account. Well, now we go to a step forward and we start with the 3D models. This is a mandible, this is a full 3D mandible, and we want, for instance, put an implant, a dental implant there. So this is just a demonstrator. In order to save computational cost, we take a part, a small part of the mandible, and we put there an implant. We invent, in this case, the boundary conditions, some little boundary conditions there, and some force applied over the implant. Well, we mesh in one side the image, and we also mesh the geometry in the implant with the technologies I explained before. Then we have the short-term implantation and the long-term osseointegration. So in the short term, what we are having is an implant that is in contact with the mandible. So here we implemented the contact model between the image and the screw. Then when the TEMS happens, the implant is osseointegrated. So this is not contact anymore, okay? Or is a stick. But what is remaining here is that we consider the same bone at the beginning and at the end. But this is not true, because when I put the implant, the bone changes. So we need also to take into account the remodeling process. Well, this is the stresses in the implant, the normal tractions in the implant when the frictional model is considered or when the complete adhesion is considered. They are slightly different. So for the remodeling process, we use the model developed by Doblare and Garcia many years ago. And well, we use this, but we can use any one. This is just an algorithm for update the image according to the, well, in this case, stress or stresses in the previous time step. Well, how it works in our context? In our context, it's really easy to implement. We have an initial image. We center in one of the voxels. We check the voxels around, and we build a kind of fabric tensor H, which give us not also the density in the voxel, but also a kind of directionality of the material. We update it for the next day according to the model that takes information from the finite element solution, and we have a new material distribution. We can do that for every voxel into the mesh, and if we run it, we obtain, after some days, a variation of the image, so we can show directly how the image varies in time. Well, here we can observe that when we apply load to the implant, of course, there are more stimulus around the implant. It appears, it happens that the bone is generated around the implant. This could be used to see if the implants will be valid for the patient, taking into account the bone of the patient, and also if we have some problems because bone disappear around the implant, that it's the moment when the implants fail. And because this is because the bone remodeling provoked that the bone disappear on the implant. Well, this is another view of the same. But what problem are having here is really difficult to find what are the loads for the implant, because this problem we invented, but we don't want to do that in the real practice. So if we want to select which is the right implant, we need to control the bone remodeling simulation. So we need to define what are the loads, and we need to know which are the parameters controlling the remodeling process, that they are mainly focused on this graph, that is a stimulus that is related with the deformations and the stresses, and a rate how the bone evolves, even if there is resorption or formation of the bone. It's something similar to topology optimization in some sense. Well, but there is a very high uncertainty in the remodeling parameters or in the loads. It's really difficult to measure the load. It's possible to measure, for instance, in a masticatory, the maximum load. But what about the load that is the person having each day, that is the one of interest for remodeling? Well, we develop a strategy for doing that in an efficient manner, we think. Well, we have one remodeling step, which is the finite element solution with some parameters coming from the, could be loads or could be their modeling parameters. And with that, we update the image. Well, if we have into account that normally the bones, when there is no fluctuation, when I want to put an implant, the bone is more or less stable. So if the bone is stable, what I will expect is if I have the right set of parameters, the bone will not evolve in time. And, well, so we define the objective function here as the evolution of the bone in time. If the bone does not evolve, that means that the image remains constant. I will be in the right set of parameters. Well, here, in order to try if this works or not, we define a problem which is under control, that is cantilever beam. This area is fixed, and I put some load in the other area. So we run the remodeling process that is similar to a topology optimization process in this context. And this is evolving time, this is stimulus, and this is density of this artificial problem. And we see that, well, we obtain some more or less standard in the context of topology optimization. Well, after thousands of days, we can say that, well, this is stable. We are in the stable bone situation. Then we run the previous algorithm. We try to do a blind search of the parameters of the position of the loads. So we run the remodeling process for 200 newtons and the location of 0.03 meters, and then the optimization process obtains the load that was generating the stable image. So we do that now for a mandible. Okay? This is a mandible that tooth is missing. Okay, and well, this is the superior maxilla, and we want to know what are the loads over the other teeth. Well, we apply some boundary conditions, some detailed boundary conditions in the violet area, and you can observe here in green the mesh that we use. So the unknown here are the loads. We assume that we know the remodeling parameters. We don't know the loads for the particular patient. Well, we define a region of interest is the region I will compare. We choose that region in this case because since we are not having the tooth, we don't have interactions in this region of interest with the teeth that, of course, will not be remodeled. So we could start asking for, well, if we have 4 teeth times 3 directions of the load, so we have 12 unknowns. So, but starting with 12 unknowns, it's really hard. We have to regularize it. How? We make steps. First, we go for the main load, which is the vertical one. Then we assume that the load is similar, and we know by bibliography that for this tooth, it's only more or less half of the vertical load from the other ones. So we optimize FZ, and we have 111 newtons. Then we define that the canning one is this one, and the last one is that loads in green. We assume that we are happy with them. Okay. So from this point, we want to improve or to update the 2 loads here in red that are closer, so have more importance to the region of interest. So again, we launch the optimization process, and we obtain two other laws that, as you can observe, differ a bit from the previous one and has sense, because this tooth, well, has less structural responsibility in the mastication process. Then we want to know if there are some horizontal loads, and this runs the third step of the optimization process, and we obtain the horizontal loads for this. And these are more or less in the quantities, or more or less in the half of the quantities of the maximum loads that we find in bibliography, that they are around 300 newtons, that it's obviously too much. These smaller loads that are applied in the we obtain them because we take a look to the bone, that is the actual response to the masticatory loads. And well, this could be used to define the actual loads over the implant that will make, or that will run, the remodeling process after the implantation, and with that we can decide if this is good or not. Well, what about the results? Here in the first line, we obtain how the region of interest varies in time if we use the loads in bibliography. We observe that the density in the region varies a lot if I run the remodeling process. If I use the optimized loads, in time, I see that the variation of the density, well, still a variation, but is smaller than the variation of literature loads for this patient. Why? Because these loads are adapted or are equivalent to the real one for that patient. And then the final example of applications of these techniques is, well, here in the first step, we make an example of remodeling process. But what happens when a bone is broken? It's not only the remodeling, it's healing. Today, well, this is a tibia. What is usual when you really broke a tibia, they put a screw of titanium, steel, and you have a surgery for putting the screw, and then for putting the implant, and then a second one for extracting it. So you have two times, you go 2 times to the quirófano, and you go 2 times to the hospital. Which is the idea we have? Well, we want to explore the possibility of changing that metallic implant by a polymeric implant that can be reabsorbed by the body. Well, and of course, well, metallic implant is really strong. There is no mechanical problems, but with polymeric implants, even they are really good polymers today, we have to take into account how the stiffness of that implant, because the stiffness of the implant, the position of the implant, or the geometry of the implant will really affect the healing process. We are in the situation of a breaking bone, and then here is the context. We have the bone here in gray, we have the callus here in red, and we have the implant that, since it's a polymeric implant and this be absorbable, it will be deteriorated in time. Also, the bone will be healing in time, transmitting the load through the bone or through the callus and not through the implant in time. So the global context is that the load will be transferred at the beginning by the implant, and will be time each day, the load will be transferred to or through the health bone. So, and all this will be running the cgFEM, since it easily deals with CT scans. I already explained the bone remodeling process before, that will take place in the long term. Now, we also develop a healing simulation tool based on fuzzy logic, because most of the bibliography of the healing process is described by fuzzy logic, which is a kind of artificial intelligence that is adjusted to the physical observations normally in sheep bones, not in human. But well, we assume that they don't differ too much. And then what is next is not developed today is to also consider the polymer degradation, but we think that this is not that a main deal, is just to change in material properties of the polymer in time. Well, we have here the medical image. We have this tibia, this same tibia here in your right hand in red. So we provoke artificially a fracture. We delayed 4 millimeters of the bone, and we define a callus region. This is the region where the callus can grow. We invent an implant, and we put the implant into the bone through, in this case, adhesion in the 2 screws on the top and on the bottom. There is no contact in this case between the implant and the bone. Well, in this case, we apply the loads, for instance, the physiological loads of the patient, and we want to see how the callus is generated in time. Here, in this video, we make 2 projections for the sagittal plane and in the in the other plane, okay, in the frontal plane, and we will observe how the bridge, the callus bridge, is generated in time. We make a zoom, and here I will only represent the density of the callus that is not zero in order to see how it grows. The color represents the density or the bone concentration. So we observe how the bone repairs after more or less, each iteration represents 1 day, it's around 60 days, the callus is formed. So it's already stable. So the implant here is each time transmitting less and less load, so it can deteriorate around in 60 days, it can start the degradation process. And what is important is that the shape of the bridge, it depends on the stiffness of the implant or on the relation on the stiffness of the scaffold. If it's really, really stiff, what happens is that since there is no mechanical stimuli, there is no healing process. If this is too loose, what's happening is that the bone degenerates and there is no healing. So the stiffness of this union between the implant and the bone has to be in a certain value in order to provoke the bone repair. With that, there are some of the publications regarding the cgFEM technology that we have been developing during the last years. And with that, I finish my presentation.
Thank you very much for that presentation. We have time for some questions, if anybody.
Can you go to transparency number 18? Because you talked about yes, you talk about the stabilization, because the gray area in the image,
yes,
is where the solid is.
Yes.
And the white area is free. So why do you have a force applied in that? Don't you have the forces applied to the?
No, this is not a force.
Right.
This is a stabilization term.
The stabilization.
Yes, here in the stabilization term, this part is more or less a lumped mass matrix that goes to the stiffness matrix. Is this spring, and this is in the right-hand side, and is a force that is calculated iteratively in order to minimize. I don't know the force. The first choice is 0.
Okay, so this is a representation of the stabilization.
Yes, that is. And this is actually, I don't care. The solution here has no energy. I have problems because there is no energy related to this degree of freedom.
But I thought you were solving those issues with the agglomeration. because this
This makes an agglomeration because this term actually is the projection of the solution, but it's not done in the same resolution, but is done iteratively because it's easy to implement. And then the stiffness matrix is constant.
Thank you.
Any other question or comments from people outside too? I was wondering. Go ahead, Manu.
Hello, very nice work. I missed the first part of your lecture. I don't know if you mentioned that. Is there any link? This is a curiosity with this the finite cell method of Rusk and his robot Munich.
Yeah, it's another way.
But it's not the same. No, they also use Cartesian measures, but I think the difference is in the interpolation.
There are differences in the interpolation. There are also differences in the stabilization methods. The differences are in details, more or less.
In details. The concept is the same. Very powerful.
It has the application in some areas. Well, if you have a CAD geometry and you have a standard finite element and you have a good measure, well, I would say it's not the best option. But when you go to medical imaging, when you go in this context, it's very powerful.
Any other comments? I had a curiosity. You mentioned that, well, you showed before that there are some stress concentration due to pixelation.
Yeah.
Can this be a problem sometimes? I mean, you said that you can limit the number of finite elements around pixel, but is this always going to solve the issue? Or?
Normally, yes, because when you include several voxels into the element, what is happening is that you are making more or less diffuse the concentrator, because at the end you integrate it, so you make it diffuse. So the stress concentration tends to disappear. Of course, you are not having the real geometry because you have a pixelization of the geometry, but you avoid the effect of the stress concentrator at least. That's why when you go more than 1 element per pixel, then you capture the concentrator that is not real. It's an artifact of the image.
Okay, thank you. Any other comment, question? Otherwise, I think we can close the seminar here. Thank you very much all for your attention.
Thank you very much.
Thank you again, Enrique, for the presentation.
Thank you very much.
Thank you. And see you in the next session in 2 weeks. Okay. Bye-bye.
Muy bien, Enrique.
Gracias.